Hello everyone, in this video I'm going to share about Introduction to Quantum Computing, according to what I have learned so far. Now let's begin. What is quantum computing? Quantum computing is a field of computing that utilizes the principle of quantum mechanics to perform operations on data. It can be used to solve certain problems more efficiently than classical computing. How and why quantum computing can outperform classical computing in some tasks are related to these characteristics: superprecision, entanglement, interference. Now first, let's compare the classical bits with quantum bits or qubits. The basic units of information in classical computing are represented by either 0 or 1. In other words, one bit can only be in one state at a time. Qubits are fundamental units of quantum computing. They are capable of representing 0, 1, or both simultaneously due to quantum superposition. It can be in many states at the same time. Here's a simple visualization for qubits and superposition. Its basis states can be 0 or 1, similar to classical bits, and these are their notations. A qubit can also be in a superposition state, where it has some probability of being measured as 0 and some probability of being measured as 1. Mathematically, this superposition can be represented as a linear combination of the basis states, 0 and 1, with complex probability amplitudes associated with each basis state. This linear combination can be expressed as this equation, where the square of magnitude of alpha and beta represent the probabilities of measuring the qubits in states 0 and 1, respectively. For example, for this particular qubit, there is a 50% chance that it can be measured as 0 and 50% chance that it can be measured as 1. Until the qubit is measured, its state remains in a superposition of 0 and 1. It's only upon measurement that the qubit state collapses to one of the basis states, and we observe a definite outcome. Superposition enables quantum computers to explore many computational paths in parallel, providing exponential parallelism compared to classical computers. Next, let's talk about entanglement. Qubits can become entangled, meaning the state of one qubit is correlated with the state of another qubit, even when they are physically separated. To illustrate this concept, let's consider a simple example of entanglement using a pair of qubits, represented by this equation. In this entangled state, there's a 50% probability of measuring the qubits as the 0-0 pair, and a 50% probability of measuring them as the 1-1 pair. If we measure one qubit in the pair and find it to be in the state 0, we instantaneously know that the other qubit is also in the state 0, regardless of the physical separation between them. Entanglement enables quantum computers to perform operations on multiple qubits simultaneously, leading to increased computational power. Now, let's talk about interference. In quantum computing, qubits are often visualized as spheres for ease of understanding, but in reality, they exist as a state described by a wave function. When qubits combine with each other, they can exhibit interference phenomena. much like waves in classical physics. This interference can manifest in two distinct forms: constructive and destructive. Constructive interference occurs when the probability amplitudes of compatible quantum states reinforce each other, leading to an increase in the likelihood of observing those states upon measurement. Conversely, destructive interference arises when the probability amplitude of incompatible states cancel each other out, reducing the likelihood of observing those states. By carefully manipulating the quantum states of qubits and designing quantum algorithms to exploit interference effects, we can enhance the probability of obtaining the desired computational outcomes while suppressing unwanted outcomes. With the exponential computational power that these characteristics give to quantum computing, the question is, will quantum computing completely replace classical computing? The current answer is no. Quantum computing is unlikely to fully replace classical computing. While quantum computing offers significant advantages for certain tasks such as cryptography and optimization, classical computing remains essential for general purpose computing and interfacing with existing systems. Additionally, challenges like qubit coherence and scalability limit the widespread adoption of quantum computing. Instead, both paradigms are expected to coexist, with quantum computing complementing classical computing in specific applications through hybrid approaches. Now, let's look at some applications of quantum computing in details. The first one is quantum molecular simulation for drug discovery. Quantum computers can simulate the behavior of molecules with high precision, enabling researchers to understand complex biochemical processes and predict the probabilities of new drugs more accurately. For example, quantum computers can simulate the interactions between drug molecules and target proteins, leading to the discovery of novel therapeutics and accelerating the drug development process. Another example is quantum annealing for optimization. Quantum annealing is a technique used to solve optimization problems by finding the global minimum of a cost function. One application is in financial portfolio optimization, where quantum computers can efficiently allocate assets to maximize return while minimizing risk. The last example is quantum machine learning. Quantum machine learning algorithms leverage the computational advantages of quantum computers to improve the training and inference process of machine learning models. For example, quantum computers can efficiently process large data sets and explore high-dimensional feature spaces, leading to more accurate and efficient AI models. Quantum algorithms like quantum support vector machines and quantum neural networks hold promise for enhancing AI capabilities across various applications. However, with its formidable computational power, quantum computing also poses significant threats to classical cryptographic systems. For instance, Shor's algorithm, which is a quantum algorithm, can efficiently factor large numbers. This jeopardizes the security of widely utilized public key encryption schemes such as RSA and ECC. However, advancements in quantum computing have prompted the exploration of several countermeasures. One notable approach is quantum key distribution, which harness the principle of quantum mechanics to establish secure communication channels by distributing cryptographic keys encoded in the quantum states of photons. It ensures that any attempt to eavesdrop on the quantum communication would disrupt the delicate quantum states, immediately alerting legitimate users to the presence of a potential intruder. Next, let's talk about the challenges of quantum computing. Quantum computing are still considered to be in its early stage, so there are a lot of challenges that it has to face. First is decoherence. Quantum systems are delicate and prone to decoherence, causing computation errors. To maintain quantum information integrity and reliable qubit operations, strict control is needed. Quantum computer currently demands controlled conditions like very low temperatures, isolation from interference, vacuum environments, precise electromagnetic control, and stable power supplies. These measures help counteract decoherence, ensuring dependable quantum computing. Second is scalability. Building large-scale quantum computers with a high number of qubits is a significant challenge. As the number of qubits increase, so does the complexity of controlling and maintaining their quantum states. Achieving scalability requires advancements in qubit fabrication, error correction, and system integration to enable the reliable operation of large-scale quantum computing systems. Third is hardware development. Developing reliable and stable quantum hardware, including qubits and control systems, is essential for building practical quantum computers. Current quantum hardware technologies face numerous technical challenges, such as qubit coherence times and manufacturing scalability. Advancements in material science, engineering, and fabrication techniques are needed to address these challenges and realize scalable quantum computing platforms. Fourth is limited workforce. There is a shortage of skilled professionals with expertise in quantum computing, including physicists, engineers, and computer scientists. Building a diverse and talented workforce is crucial for advancing quantum computing research and development. Addressing the workforce shortage requires investment in education, training programs, and interdisciplinary collaboration to cultivate the next generation of quantum computing experts. And last but not least, quantum computing research and development requires substantial financial investment due to the complexity of the technology and infrastructure needed. Building and operating quantum computers, as well as conducting experimental research, can be costly endeavors. High cost may limit access to quantum computing resources and slow down progress in the field. Addressing cost challenges requires strategic investment, collaboration between academia and industry, and the development of cost-effective technologies and methodologies for quantum computing. These are the references that I studied from for preparing this presentation. There are a lot more interesting information in these links that I think you might want to explore more about quantum computing. Thank you for your attention.